Hey everybody, for our last video for the time being, I wanted to describe the branch and bound method. Branch and bound is a way to solve many different problems arising in computer science, but in particular, we'll talk about how you can use the branch and bound ideas to solve integer linear programming problems. So roughly speaking, you have an integer linear programming problem as I've sketched here. And in the branch and bound method, you're going to divide and conquer. So you'll sort of split your problem into two, and then you'll like explore this tree on the right-hand side, and only later come back and explore this tree on the left-hand side. So we'll go through this specific example, and we'll walk through the tree. Our walk will, do something like this. We'll walk along this tree and see what we learn about the optimal value of this problem as we go. So the images and this content is taken from Mustafa Salibi Pinar, and I've included the link to these notes where I've taken this example and the images. So we're going to maximize negative x1 plus 4x2. So that points in this direction. So these red lines that I'm drawing are like the level sets of the function we're trying to optimize. So I'm trying to move that red line as far as I can in the upwards direction to maximize this. Subject to the following constraints. So negative 10x1 plus 20x2 is at most 22, and 5x1 plus 10x2 is at most 49. We also have that the x1 coordinate is at most 5. Both coordinates are non-negative. And what makes this problem hard is that we want an integer solution. Okay, so we're looking for a solution on these blue integer lattice points that lie inside the feasible region. Most integer linear programming problems that can't easily be solved by relaxing them are often solved by some variant of branching and bounding. So this is an important method for integer problems. The main observation that we'll be using is, let's say I wanted to look for an integer solution on the right half of this line or an integer solution on the left half of this line. Okay, well, there's this whole bit in the middle where there's no integer solutions at all. So I can do slightly better than just dividing this at 3.5 and looking at the solutions greater than or equal to 3.5 and less than or equal to 3.5. Indeed, if I require integer solutions, I could instead just look at all integer solutions greater than or equal to 4 or less than or equal to 3. You see that? So the nice observation is that when you subdivide, you can subdivide with extra width. And you want to use that extra width so that when you consider smaller linear relaxations, you're more likely to end up at an integer solution. Okay, so since the x coordinate is an integer, it's either at least 4 or at most 3, right? It either lives to the right of this line with x1 value 4, or it lives to the left of this line with x1 value 3. So that's our first split in the tree. And we're going to explore the right half initially, and then return back to the left bit. Okay, so let's first explore the right side. What you do is on this region that's now smaller, we consider the relaxation. So we consider not only finding integer solutions, which is hard, but just find any solution. That's quite quick. Use the simplex algorithm. So we use the simplex algorithm and we find this is the optimum, right? This point is the furthest in that direction. The coordinates are 4, 2.9, and the value is 7.6, okay? One comment, 4, 2.9 is not an integer solution, right? This is not a lattice point. So we haven't really found a candidate solution yet to our problem. It's not even integer coordinates. But notice that doing the split, not at 3.5, but instead at 4 and 3, it at least made the x coordinate integer, right? So as you do these splits along integer coordinates, you're sort of promoting that it's more and more likely to get more and more integer coordinates in your solution. So we're still just considering only the right-hand side. We're now going to do a split in the x2 direction or the y direction. So we're going to split, think of doing the split at 2.5, but really you can think of doing the split at less than or equal to 2 or greater than or equal to 3. All right. So since x2 is an integer, it's either at least 3 or at most 2. It turns out that when I look at the part at least 3, it's infeasible. There's no solutions. And you find that with the simplex method very fast. Okay, so I still have this constraint, x1 is at least 4. I add in this constraint, x2 is at least 3. No feasible solutions. Okay, but if I still have this constraint, x1 is at least 4, and now I add in the constraint, x2 is at most 2, I do have feasible solutions. I solve the just standard relaxed problem, and I happen to find an integer solution. Okay, so I sort of promoted that might be likely to happen based on where I did my cuts. But I do find that the best solution over all the integer ones and the non-integer ones in this rectangle here is at the integer 0.42, and the value of the optimum is 4. So we found our first viable solution with integer coordinates. And pay attention to this value 4, because later, if we're exploring different parts of this tree and we're only finding worse solutions, we can just ignore them. We don't care. We know we can do at least as good as 4. Questions so far? We are done exploring the right half of our tree, and now we'll go to the left half, which we'll have to explore that half a little bit deeper. The website page from which I'm drawing this material does a nice job of highlighting in blue the region that's found your best candidate integer solution so far. So let's explore the left side where x1 is at most 3. So you just solved the relaxed problem, forgetting about the integrality constraint, and we find this non-integer solution, 3, 2.6, that has value 7.4. Okay, 7.4 is better than our value 4, but we can't provide 7.4 as a solution yet because it's not an integer solution, right? The inputs are not integers. So that means we need to keep exploring this tree. Let's subdivide with the second coordinate at most 2 and at least 3 as we did before. So we branch again. Since the second coordinate is an integer, it's either at most 2 or at least 3. If I cut above 3, I get this empty region. So no need to further explore. Let's cut at most 2. On the left side, I cut the vertical coordinate to be at most 2. I solve the relaxed problem, ignoring the integrality constraint, and I achieve this solution, 1.82. It has value 6.2, okay? I can't yet achieve 6.2 with an integer solution, but I know this is at least still worth exploring. There could be an integer solution in here that has value better than 4. So we're going to split again on the x1 direction. Since x1's an integer, it's either at least 2 or at most 1. Okay. Let's consider first the bit that's at least 2. It has an integer solution. Well, when I solve the linear programming problem, I find the solution that happens to be an integer one. It has coordinates 2, 2, and value 6. That makes me really happy. I found a new integer solution, 2, 2, that has a better value than any integer solution I've seen so far. 6 is our current best integer solution. And, you know, generally when you solve relaxations, you don't necessarily find integer solutions. But here we promoted that because we did these cuts, extra cuts along integer lines. So keep track of, you can forget about the number 4 now. 4 is old news. We don't care about 4 anymore. 6 is our new best value, and it's obtained at the integer point 2, 2. We still need to consider the part where x1 is at most 1. We solve this relaxed problem. We find a non-integer solution, and its value is 5.4. Okay, 5.4 is worse than 6. I already found an integer solution that has value 6. Here, this entire region, the best I can do is 5.4, whether or not I even find an integer solution. But clearly, I'm not going to find an integer solution that beats 6 because I can't even beat 5.4. So this remaining portion of the tree is called fathomed. You've explored it as far as you need to go. You've explored it enough to say no solution here is better than what I've seen so far. Okay, great. So hence this optimal solution over the integers in this entire domain is 2, 2, and the value is 6. And this is a really nice method, right? Integer solutions often don't live on the boundary of these polytopes like typical solutions do. And so it's hard to find integer solutions, but through this method of cutting iteratively, we've proven that this is our best solution. So in general, exploring these trees can really speed things up, although in the worst case, you might have to explore every branch and leaf of that tree, and it can take a while if you're unlucky. Let me review again the logic. We had this integer linear programming problem. We split, and when you split, you can split with a width and in a way that promotes finding later integer solutions. Okay. So first we went down here. On the right-hand side, we found some value, but it was a relaxed value. It wasn't achieved at integer coordinates. And then we split again at 2 and 3. Above 3 was infeasible. There was nothing on the right-hand side above 3. On the left-hand side, below 2, I guess here, we found our first integer solution, and it had value 4. Okay. So then we sort of went back to the left-hand side. Now we need to explore everything where the x1 coordinate is out at most 3. We did the relaxed problem, and we got a non-integer value, a non-integer solution with value 7.4. Since 7.4 was at least 4, that's why we continued. If we got a number here that was less than 4, we would have just stopped. Okay. So then on the left-hand side, we split again above 3 or at most 2. The values at least 3 were infeasible, so we ignored that. And then we went down here. So we're looking to the left of 3, at most 2. And we found a non-integer solution with value 6.2. Since 6.2 was at least 4, we continued. We cut again in the x coordinate to the right and to the left. Okay. And then when we explored the region to the right, we found this integer solution with value 6. And then on the left, we found a non-integer solution whose value wasn't even as good as the integer one. So we no longer had to explore the left. And in that way, by traversing this path, we have sort of computationally proven that we found an optimal integer solution to this problem. Questions?
Hi, Henry. I have a question.
Yeah.
This is a really cool algorithm, but I'm just wondering if, like, combinatorially, it's guaranteed to be faster than just checking all the lattice points to see whether or not they're in the feasible region, and then uh, computing the value to find the optimal one.
Yeah, so in practice, it is much faster because I think it's like maybe even like if you think of the naive algorithm as linear in terms of the number of lattice points, right? Checking each lattice point. I think this algorithm is probably going to be logarithmic on average in the number of lattice points. Now, don't quote me on that. That's just a guess. Optimistically, you might hope for a logarithmic algorithm when you're dealing with trees. Um, in the worst case, it's going to be the same as the naive algorithm, right? In the worst case, your cuts are such that you have to explore every single lattice point, right? So worst case, it's no better than the naive algorithm, but in the average case, it's going to be way better. The reason why you should expect that you might be able to do even as good as logarithmic is, this is a binary tree, right? So um, it's like every new row can have twice as many entries as the row above it, right? We had 4 and then 2 and then 1. So whenever you get to a spot where something's infeasible or where you fathomed the rest of that subtree, you no longer need to keep exploring, right? So whenever you have these red nodes, as I've labeled them, where you don't need to keep exploring, or even the blue nodes where you don't need to keep exploring, you've cut out on a lot of lattice points to check. So that's why you might, the naive algorithm you could even draw as a tree where every solution is sort of at a leaf. Right. So when you're doing the naive algorithm, you can almost think of it as traversing this tree. And the point of this algorithm is that you cut off many of those possible lattice points that otherwise you would need to individually consider, just because they've already been bounded by an integer point that's better, or they've been bounded by a possibly non-integer point that's worse than a known integer point. I'll
Yeah, that's
stop.
cool. Thank you.
Okay. Yeah, yeah. So I regret not getting to this until the last day of class. I think I sometimes get scared about computational things, but this is just a beautiful algorithm. Again, it's an instance of why didn't I think of that myself, 3 weeks ago when I was teaching this class. Well, uh, I don't know, but it's really cool. I think it's a very appealing algorithm.